Capacitance and capacitors. We're now going to take everything we've learned about electric field and electric potential and apply it to a real working circuit element. The simplest version of a capacitor is the parallel plate capacitor, and you'll recognize this looks just like the infinite parallel planes that we did in the last chapter. We have two metal plates, they're parallel to each other and located a small distance apart. We now connect a battery to the two plates. Charge moves between the two plates, and actually we haven't shown you what the symbol for a battery is yet, but this is a battery. We'll cover that in the next unit. Horizontal lines, long, short, long, short. Or you could just do two of them, or you could do six. I like using four. So this is a battery, which is a source of electric potential. What happens is the electrons on this plate get attracted by the positive terminal of the battery. The longer line is the positive terminal. They go through the battery and they get deposited on this plate. So by moving a negative charge here, you leave behind a positive charge here. And we call that a positive ion. If you lose an electron, you're an ion. So this is not a proton, but that's a positive ion. The plates, as you can see from just the one electron moving, they have equal magnitudes of charge, but one is positive, one is negative. Notice, nothing's going between the plates. In this air here, this space, it goes through the wire. We let this go for a while until you see a number of positive ions up here, and actually, of course, they're spread out over this entire plate, but we're just showing the edge. And a number of electrons. For every positive ion, there's one electron, so the total charge stays neutral on the capacitors. Most of the atoms are neutral since they have equal numbers of protons and electrons. This is just showing the ions and the electrons, which depend a lot on what voltage you put here and other factors that we're going to go into shortly. Hopefully you noticed on the previous slide these blue lines. What are these guys? Those are the electric field lines. And since we did so much work on the infinite planes, we did that to show that the field is uniform between the planes. So the electric field is uniform everywhere within the capacitor's gap. Also, there is no electric field outside the gap. You see we didn't draw any blue lines anywhere over there. How does this relate to the work done in the previous chapter on the parallel infinite planes of charge? Here's the drawing from the last chapter. These were two infinite planes. You can recognize the voltage symbols there. And we assumed that they were of infinite size, and that told us that the electric field was uniform between the planes, and also there was no electric field outside the planes. We are now making the same claim for this capacitor, which has a finite size. The parallel plates of the capacitor have a finite size, but they're designed so that this plate size is very, 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 very much greater than this distance between the plates. So if you're a charge anywhere around here, you think you're sandwiched between two infinite planes. So the capacitor properties are very close to the infinite plane case. And once again, the charge separation over here is caused by the battery.